11:40 at night on a long downhill grade in mountain country. A freight train is doing 60 miles an hour and the engineer just pulled the brake handle for a routine speed check heading into the descent. The train doesn't slow down the way it should. Not nothing, some response, just noticeably less than it needs to be. Right now. On a grade that's about to keep adding speed for the next 11 miles. Whether the train wants it to or not, gravity doesn't care what the brake gauge says. It just keeps pulling. Here's the reveal I want to get out of the way immediately, because it changes how you'll listen to everything else in this video. A train doesn't have a brake, it has dozens of them. Spread across every single car, running through at least 3 or 4 completely separate systems that don't all depend on the same parts, the same air pressure, or the same piece of equipment failing at the same time. When people hear the brakes failed, they picture one lever connected to one mechanism, just not working. That's almost never what's actually happening. What's usually happening is one layer of a much bigger system getting weaker, while several other layers are still sitting there, untouched, waiting to be used. So the real question tonight isn't can this train stop, it's how much of that layered system has to disappear before 60 tons of steel per car, multiplied by however many cars are behind that locomotive, becomes something nobody on board can control anymore. If you watched our video on cargo ships a while back, you already know those massive vessels genuinely have no brakes at all. In any form you'd recognize, trains are almost the exact opposite problem. They have brakes everywhere, redundant on top of redundant, and today we're finding out exactly what has to go wrong. How many separate systems have to fail at once before a train actually becomes what railway engineers quietly call, with more dread than the term suggests, a runaway? Start with the part almost nobody thinks about, because it's the reason a single brake lever at the front of a mile-long train was never going to work in the first place. A loaded freight car can weigh well over 100 tons. String together 100 cars behind one locomotive and you're looking at a train that can stretch past a mile long, carrying more weight than a decent-sized cargo ship. Trying to stop all of that using one mechanism at the front, connected by some kind of cable running the entire length of the train, was never physically realistic. So instead, trains use something that sounds almost too simple to work: air. Every car has its own brake cylinders pushing pads against the wheels, all controlled through one continuous line of compressed air running the length of the train. Drop the pressure in that line, and every car's brakes engage simultaneously, no matter how far back they are. Here's the part that deserves more credit than it gets. The system is built so that a loss of air pressure, for any reason at all, whether it's a deliberate brake application or an accidental line rupture from a car separating, automatically triggers the brakes to engage, not release. If the train breaks apart, both halves break on their own without anyone touching a control. That failure mode is the safety mechanism. Now, the wheels themselves, steel on steel, is fantastic for reducing friction. While a train is moving forward, which is exactly why trains are so efficient, that same low friction relationship becomes a problem the second you're trying to stop, because there's only so much grip available before something gives. Push the brakes too hard, and instead of a wheel continuing to rotate while slowing, it can lock completely and slide along the rail like a hockey puck, grinding a flat spot into a multi-ton steel wheel that then has to be pulled from service. So every modern train runs wheel slide protection, functionally almost identical to the anti-lock brakes in your car. Sensors constantly monitor how fast each wheel set is actually rotating. And the moment one starts sliding instead of rolling, the system automatically eases pressure on that specific wheel set, then reapplies dozens of times a second without anyone in the cab doing anything except holding the brake handle in position. Asking for maximum brake force doesn't guarantee maximum stopping power. It just guarantees the system will use as much force as the wheel rail grip can handle without sliding, and not one bit more. Here's why speed changes this entire equation so dramatically. Kinetic energy doesn't scale with speed in a straight line, it scales with speed squared. Double your speed and you don't have twice the energy to remove, you have 4 times as much. A train doing 30 miles an hour and the same train doing 90 don't have a mildly different stopping problem, they have a completely different category of problem. At 200 kilometers an hour, a train is covering roughly 56 meters every single second. That's the length of a football field disappearing every 2 seconds. Every moment an engineer spends confirming what's happening is already hundreds of meters of track gone. Our train on that mountain grade doesn't just have existing momentum to fight either. Gravity keeps adding more of it the entire way down, which is why long descending grades get treated as their own specific engineering problem, separate from ordinary stopping math. This is also why trains have a second braking method that doesn't rely on friction or air pressure at all. Electric and diesel-electric locomotives use motors to turn the wheels forward, run those same motors slightly differently, and instead of pushing the train, they resist its rotation, acting as a brake instead of an engine. This is dynamic braking, and on some trains, the energy generated this way actually gets sent back into the electrical system rather than wasted as heat. It won't bring a speeding train to a dead stop entirely on its own, but it's a genuinely independent method of shedding speed, which is exactly why crews lean on it hard during steep descents, protecting the friction brakes for when a full stop is actually needed. So with all this redundancy, how does anyone ever end up in a genuine runaway? A CSX freight train, locomotive number 8888, was sitting in an Ohio rail yard in 2001 when the crew stepped off to deal with a switching issue elsewhere. Somehow, the brakes released and the train started rolling. Nobody was on board. It picked up speed, entered the main line, and kept going unmanned, hauling dozens of cars, some carrying hazardous chemicals, through populated towns in northwest Ohio for close to 2 hours, with news helicopters tracking it live as it pushed toward 50 miles an hour. With nobody at the controls, with everything we just covered. Why didn't any of those systems stop it? Because none of them were ever engaged in the first place. This wasn't a brake failure trying and coming up short. The brakes simply weren't applied the same way your car doesn't stop on its own. If nobody's pressing the pedal, all that redundancy only matters once someone or something actually calls on it. The solution railway crews landed on that day is genuinely satisfying in how mechanical it is. A second locomotive, crewed by 2 people, chased the runaway down, matched its speed, and physically coupled onto the back of it while both trains were moving. Once connected, they used their own brakes to gradually drag the runaway to a stop from behind, like grabbing the back of someone's shirt while they're running, and slowly leaning back until you both stop. It worked. Nobody was hurt. The story became well known enough that it directly inspired a Hollywood movie a few years later. That's the version with a clean ending. The next one is the version where several safety layers failed at once, and it's the reason a huge amount of modern rail safety regulation exists today. In the summer of 2013, a freight train carrying crude oil was parked for the night on a slight grade outside a small town in Quebec, left unattended following standard procedure at the time. A fire broke out in one of the locomotive's engines, and firefighters responding shut that engine down as part of standard fire response. Not realizing it was also what maintained air pressure to the train's brakes. The handbrakes that had been set as backup weren't sufficient to hold the full weight of the train. Once that air pressure disappeared, the train began rolling on its own, unmanned, down the grade toward the town of Lac. It derailed in the town center. Several tank cars ruptured. 47 people lost their lives that night. I won't dwell on the details beyond that, because the human cost deserves weight. Not dramatic narration. What matters here is what changed afterward. Because this is the story of an entire industry looking at every layer we've discussed tonight and asking which one should have caught this. The investigation found the handbrake backup, the layer meant to hold a train secure, with zero reliance on air pressure, hadn't been applied with enough force. For a train of that weight on that grade, regulations around how many handbrakes must be set and how that's verified got significantly stricter afterward. Rules around leaving trains unattended on grades tightened. The tank car design used that night was identified as more vulnerable to rupture in a derailment, and a phase-out began soon after. Here's the actual lesson underneath it. Every system we've covered, air brakes, wheel slide protection, dynamic braking, assumes a moving train, with an engineer present, actively managing speed in real time. Lack happened in the one scenario those systems were never built to directly address. A train sitting still, unattended, relying entirely on a backup layer that turned out not to be strong enough for those specific conditions. The chain of protection ended at a link nobody had stress-tested hard enough for that exact situation. That's exactly why there's one more layer worth understanding, one that doesn't live inside the train at all. Modern railways increasingly rely on automatic train protection, generally grouped under names like etceteras in Europe, PTC in the United States, or CBTC on urban transit systems. The technology varies, but the idea is consistent everywhere it's implemented. The railway itself constantly tracks exactly where a train is, how fast it's moving, and what speed it's actually permitted to be doing on that stretch of track. If a train exceeds that speed or continues toward a signal, it should have already stopped at. The system can apply the brakes automatically without waiting for a driver to notice and react. It's the railway equivalent of your car recognizing you're about to run a red light and quietly taking control of the brakes itself, faster than you could have reacted. There's a broader piece most people never consider too. The railway doesn't only try to stop the train that's having a problem. Signal and traffic control can simultaneously hold every other train on that line in place, keeping conflicting routes clear, making sure that even if one train genuinely can't stop in time, it isn't going to encounter anything else on the track. Sometimes the goal isn't stopping the runaway instantly at all, because depending On speed and grade, that might not be physically possible. The goal is clearing the surrounding railway of anything it could hit, while whatever's left of the braking system does what it can, for as long as it takes. Back to our engineer on that mountain grade, because I never told you how that one ended. The reduced brake response wasn't a total system failure. It was one specific issue. A slight loss of air pressure efficiency on one particular car. Full braking capability was still available everywhere else. He made an emergency brake application, which triggers a stronger, faster pressure drop and engages every car's brakes at maximum force simultaneously, combined with dynamic braking already active from the locomotive. The train's speed came down within the distance available, well before the grade leveled out. Routine enough that it barely made it into a maintenance log. That's the most common version of this story, by an enormous margin. Not a runaway, just one layer of a much bigger system doing exactly what it was built to do, quietly, while several backup layers sat there completely unused. So here's the actual answer to the question. In the title. If a train's brakes stop working, it depends entirely on which brakes, and how many separate systems that failure actually reaches. Losing one layer rarely means losing the ability to stop at all. Losing several at once, especially in situations those systems weren't specifically designed around, is the rare scenario where things go seriously wrong. And in the genuine worst case, where essentially everything has failed simultaneously, momentum doesn't disappear because a system failed, it has to be absorbed over distance by whatever's still fighting against it, whether that's a second locomotive chasing a runaway down in Ohio or a town that never should have had to be. The thing that finally stopped a train nobody was driving. Next time you're standing on a platform watching a train glide in and stop exactly where it's supposed to, without so much as a lurch, it's worth remembering what you just watched wasn't one brake working correctly. It was an entire layered system built by people who assumed something somewhere would eventually go wrong and made sure one failure was never going to be enough to end the story badly. If this changed the way you think about the trains crossing tracks near you every day, subscribe to Valnor. There's a lot more hiding inside the machines quietly running our entire world, and we're just getting started.